So today we are going to talk about a very important building block, which is the MOSFET, right? And we have talked a little bit about it, that what is a MOSFET. So we have seen different, how we say, root or different flavors or different functionalities of this MOSFET. In this particular video, I would walk you through that what results in those functionalities, right? What is the physics or what is happening inside the MOSFET, which is making it behave like the way it behaves, right? Because similar to a human, a lot of things are going on in our mind that reflects the way we behave or talk to a person. Similar to that, so in this MOSFET, you see, and this is the symbol, right, of MOSFET typically we draw. And it is not very far from the real structure. So if you were to map this to a physical structure, because this is still a logical quantity, right? Logical representation. Logical representation means it's not the physical representation. It's a symbol. It's a kind of, we say, okay, this is the institute, and you make a logo of the institute, which is a logical representation of the institute. But when you come, you see the building, that is the physical, that becomes physical representation. So physical representation mean that now how actually this would be made in real life. So then we see, typically anything we are making, we have to, because we cannot hang it in the air, so we have to make on some base, right? Similar to whatever you are making, you have, let's say, your chair, there is a base, everything is there a base, right? Because we cannot hang this in the air, so there is a base. And this base, no gases. What is this base? This is what our favorite material called silicon, right? And why silicon? This is for topic for another video. Why silicon? For now, the importance is that this is the base, which would serve as a substrate, we call it, right? On this substrate, now obviously no gases, because there is a semiconductor and silicon is a semiconductor. So this is also in MOS, this is also the semiconductor, right? So MOS means, if we see MOS, metal, oxide, and semiconductor, right? Field effect transistor. And that is how we are going to draw the structure also, right? So metal, we have drawn the semiconductor, which is also serving as a substrate. Very good, good for us. Then we can put an oxide on top of that, which is an oxide. Then on top of that, I put a metal, right? And what is this metal? This is like this terminal, which is our gate terminal. What is this doing? This is the control knob, which we have seen, right? This is your control knob in your tap. Okay. So one thing we see, why is it a good control knob? Because there is no current, ideally, because if there is an oxide, there is no current which should flow in this direction. So this should be very, very close to zero, right? Much, much lesser than what is the operating current of your transistor. That would mean that now you have designed a very good control terminal. So that is the first constraint you see, which is coming directly from the structure, that there is an oxide or dielectric in between, right? Now, what happens is, there is where, then if the current is not flowing in this direction, where does it flow, right? Where is the control terminal actually? What is it controlling, right? If there is no flow. And that is what this field effect comes, field effect transistor. So where is the field then I would apply, right? What field am I talking about? So that means the other direction we can see is this direction in which there could be a current flow. Now to flow the current in this direction, what do I need to do? Obviously, first thing I have to do is to put contacts so that I can apply the voltage, right? And these contacts are similar to, in the symbol, source and drain, which is our source and drain, right? We also discussed there is another terminal of this, which we know as the body. The guess is for body, because that is the body or substrate is your this type, right? So now that is how we can see that we built the basic tenets of the transistor. So one of the thing which you see, if we want to make the current flow, you can definitely make the current flow. That means you have a contact. If you put a VDS, there is a finite VDS. That means VDS is not zero. And this is the current which we are talking about. IDS will not be also zero, right? It would flow. There is a current which is going to flow. How small or high this is, that is a different question, right? So now let's go back to our analogy so that we can understand it well. This is our tap. In the tap, we said, okay, there's a control terminal of the tap, right? Now, this is flowing or not depends on this control terminal, right? So in this case, we are saying when we apply a VDS, VDS is similar to applying a potential difference. That means you have water here, right? And there is no water here. Similar to that, if you apply a potential, you are basically creating a potential energy difference, right? So VDS not zero means there's a potential energy difference in lateral direction, right? So lateral means this is the direction from source to drain. That is the direction. You have created a potential energy difference because you have applied a potential, right? That is what basically it does, right? Potential. Similar to when you jump, right? You are applying any force. You would be able to see that you have increased your potential energy, but due to gravity, you come back. Similar to that, here we create a potential energy. Now, what is current? Current, as we have seen, and we can also have a small video. You should post in comments if you need that video. Current is flow of charge, right? That is current for us. This is the flow of water here. That is the, what we say, the flow, right? Water flow. But this is made of droplets which are flowing, or the water which is flowing, right? So here, so basically we can see this is flow of charge, or rate of change of charge. Means flow means it's a how much charge is flowing divided by time, right? That is my current. So now this charge, what is charge? Which charge am I talking about? These are your electrons which are flowing from left to right, right? So that means if we see this electrons, that means electrons should have been pushed from one of the terminals, and then they are taking their journey from this to this terminal, right? That is what is happening. So a journey is taken by, so the current is basically coming from journey of electrons from one terminal, which could be source, to another terminal, which could be, that is what is giving you this current, right? Interesting. So that means current is actually flowing in the semiconductor, obviously, and from the application of the VDS. If there is no VDS, VDS is zero, there is no journey of electrons, right? Journey of electrons means there is no net journey of electron, that you would not see any current flowing through the transistor, right? So now what controls the journey of electron? It's basically like this control law. What controls? And we have seen from the application that gate controls the journey of electrons, right? So now gate control the journey of electrons. Wow. So what does it mean, gate control? That means now if I have a gate voltage 0, which is what we were talking about, we said there is no IDS is very close to 0. This is what we saw in the functionality of the switch. That is a good switch. And when VGS is some positive voltage, high voltage, right? Let's say plus 5 volt, you have IDS, which is finite, right? Or appreciable. Finite means it's much greater than 0, or somewhere, let's say, if we were to name this would be somewhere in milliamps or microamps, right? Few microamps to milliamps. That is what we are talking about. So that means now that if this journey of electron I have to control using the gate terminal, what is it doing internally? So for that, I need to understand what is gate doing. So let's just understand the gate first. What is gate doing? So gate, it looks like this, right? And we are going to look at in a very nutshell what is gate doing, right? So this was our base on which we put this metal and semiconductor, sorry, metal and oxide layer. This was our base. So this is our semiconductor, right, which is silicon. So what is happening is when Vg is equal to 0, what is the condition of silicon? So that depends on what was the initial condition of silicon, because that means you have not applied any field, right? Sorry, you do not applied any voltage. That means now what do I understand what is happening in this particular stack? So when we see this metal and we see a semiconductor on the other side, and then there is a body terminal here, you could actually think of this as a one capacitor network, right? That means, and this is some capacitor, right? That's it, CG, which is the capacitance. Because capacitance is coming because there is a metal plate, there is an oxide, and then there is a another kind of, which could be a conductor here, right? Because there is a body terminal, right? And then there is, this is what of the equivalent capacitance of the stack is there, right? So now what is that I'm going to do? When I apply any positive volt, or there is no voltage applied, there is no field, that means the charge across the capacitor, whatever comes, is 0, right? Whatever charge we are talking about, which we say, let's say QG, is 0 for VG equal to 0. That is the basic capacitor action. And we can talk about that also, put it in the comments, just about capacitor, how the capacitor works. So now similar to that, what we see is here, when you have VG equal to 0, there is no charge which you are going to get unless there is already some charge in the semiconductor, which could be there, right? So traditionally, conventionally, these things which we were building with, we had this semiconductor which was already something had some positive charge, right? Which is what we called as the P silicon. Okay. And this we'll talk in detail about what is this meaning. But it was having some little positive charge. So that means now when it is a positive charge, you see current, because what is happening to the electron, it sees, oh, I want to go like this because there is a guy calling me here where I have applied VDS to be positive, right? And let's say this is, so it's basically like this. You know always that the current flows in a loop, right? So there is a battery which we have applied, right? There is a positive terminal is this. So this is your VDS. So that means now electron are going to go this path, right? Going this one. Now, suddenly when you see a positive charge in between, it's saying, oh, I have come to the foreign environment. This is something which is not known to me. Or it is basically that it is going to face a lot of resistance because there is a positive charge here, some positive charge here. So your electron is going to face a lot of resistance, right? Because it is going into some other environment, right? It is a positive environment. While it likes something where you will think that it would like to have some negative charge already lying there, then it would feel, oh yeah, this is something known for me. So that is the case when Vg equal to 0, charge is not there. You have high resistance faced by electron going from source to, oh my God. How do we solve this problem? What do we do? Right? How do we make electron flow nicely rather than it does not face this resistance? The answer to that is, if we get a positive rather than positive, if we get a negative charge here, then the electron will feel much at ease because it knows that environment of having a lot of electrons as friends there. So for that, now our capacitor says, okay, if that is the case, then why don't you apply a positive voltage here? Then I'm going to get positive charge on this plate, and on the side of your semiconductor, you are going to get negative charge. Great, right? So I'm going to get now negative charge here. Wow, just because of the capacitor action. And then it is a much easier job for electron to go through this path, right? But you could ask, okay, electron is going, if it is going from source, but what about you have changed the settings of this transistor here wherever there is gate. But what about this part where there is no gate? In this part, what do you do? So that is what we make a change in the structure. That means because our job is to only control this part. That is what is giving us the switch operation. So even if we make this part intentionally negative charge, some negative charge we can put in some pockets, right? Initially, even in the structure, which we know as the N type pockets, N silicon. This is also N silicon. N means there is negative charge already, right? P means it's a positive charge, which is there. So now in this pockets, if even if the gate is 0, you see there are two settings. You will see that when there is was positive charge, which was the initial case, when no, still your electron, it can come very nicely till here, right? So your electron can come very nicely till here because it sees the nice environment, but after that it faces a resistance, right? Now once you put in this positive charge instead of negative charge, then you see now electrons can flow there also, right? Nicely, and then it can go back to like that. It can flow from left to right. So that means now what you have done is lowered the resistance under the gate by applying positive gate voltage. Okay, so that is the basic operation. Why what you see that you have when you apply higher voltage, then you get higher currents. When you apply lower voltage, that means you apply 0 volt, you face electron face a very high resistance. Now what is happening, or what are the, when do we say that this is on off, is another question which we will look at next time. Something called threshold voltage. What is a threshold voltage in this transistor, right? So this is a topic for our next time. I hope that this explains the physical structure of MOSFET, what we talked about, and also the basic operation, very basic operation of a switch, what is happening inside the MOSFET. Thank you. See you and happy morning and keep learning. Bye bye.